A very good morning. In previous lecture हम लोगों ने देखा in transmission line the resistance, capacitance, inductance and transconductance are distributed throughout the length of transmission line. Hence transmission line is called distributed network. आज के क्लास में we are trying to find the voltage and current expressions in transmission line. Let us consider an infinitesimally small section of transmission line and all the primary constant R, L, C and G are distributed throughout the length of transmission line. We have considered a very small sections of transmission line whose length is delta x. The length of transmission line is delta x. The primary constant of transmission line are R, L, C and G. And these parameters are defined per unit length to minimize the effect of transit time. Since delta x tends to 0, or we can say that the length of the transmission line which we have considered is infinitesimally small, so the resistance is equal to R delta x for length of transmission line delta x, and inductance is L delta x for given length delta x, and capacitance is C delta x, and transconductance is G delta x. Let us consider sinusoidal voltage of angular frequency omega is applied at point A dash, and the current is moving or flowing into the terminal A. Now the voltage drop, if you look at this picture, the voltage drop you will experience at these two series element, and current will drop across this shunt element. Let us the voltage and current at BV dash be V plus delta V and I plus delta I. So voltage drop, if you are trying to calculate the voltage drop across this section of transmission line, then the voltage drop is given by drop across resistance, then voltage drop across inductance. So delta V is decreases, delta V is negative here, since the voltage at point A dash is greater than the voltage at point BB dash. So delta V is negative. Similarly, if you are trying to calculate the current drop or change in current, so change in current is given by minus G delta x plus J omega C delta x into V. If we calculate delta V upon delta x, then delta V upon delta x is equal to minus R plus J omega L into I, and delta I upon delta x is equal to minus G plus J omega C into V. From this equation we can say that these equations are the coupled equations. These equations are coupled first order differential equation. So these equations are coupled first order differential equations. If we consider the length of transmission line delta x tends to 0, in that case we may write delta V upon delta x is equal to dy by dx. and delta I upon delta x is equal to di upon dx. Equation 3 and equation 4 are the two coupled first order differential equation. If we are trying to solve this equation, so for that purpose we have to decouple that equations. Then again differentiate equation 3 with respect to distance. So this is equal to delta d2v upon dx square is equal to minus r plus j omega l into di upon dx. From equation 4, substitute the value of di upon dx in these expressions. Then you will find that the second order differential equations will find with respect to voltage d2v upon dx square r plus j omega l g plus j omega c into v. Here we assume gamma square is equal to this one. So d2v upon dx square is equal to gamma square v, where gamma is equal to under root r plus j omega l plus g plus j omega c. So propagation constant, gamma is propagation constant. This propagation constant depends upon the primary constant of transmission line as well as operating frequency. Similarly, we can find the second order differential equation in terms of current. So d2I upon dx square is equal to gamma square I. It is interesting to note that the both voltage and current are governed by the same differential equations. So the next target is we are trying to find the solutions of this second order differential equations. As I already discussed, gamma is propagation constant. It depends upon the primary constant as well as the operating frequency. So for given frequency, if we consider for given frequency, the gamma is constant. So the equations 8 and equation 7 and equation 8 are homogeneous equations with constant coefficients. Now we are trying to find the solutions of this homogeneous second order homogeneous equations. The solutions of the second order homogeneous equations can be written as v is equal to v plus e to the power minus gamma x plus v minus e to the power plus gamma x. Similarly, for current, it is given by these equations. If we are trying to calculate the instantaneous value, so to calculate the instantaneous value, we have to multiply the voltage and current expressions by the term e to the power j omega t, where v plus, v minus, I minus are constants. So after multiplications, the voltage and current expressions will look like this, where we already told you that gamma is propagation constant and gamma is a complex quantity. It is equal to alpha plus j beta, where alpha is attenuation constant and beta is phase constant. So the voltage expressions is obtained like this after substituting the value of gamma is equal to alpha plus j beta in previous expressions. From this we can say that voltage and current are complex in nature, and the phase of this voltage or current is function of a space as well as time. So if you consider the phase of voltage and current, then phase is equal to omega t minus beta x plus phase of v plus. Since v plus, this constant is also a complex quantity, so we have added the phase of v plus. If t is equal to constant, if t is equal to constant, then we can say that the phase is vary linearly with respect to distance. And if we freeze the space, then we can say that the phase is linearly with respect to time. If we consider the real part of e to the power j omega t minus beta x, this is equal to cos omega t minus beta x. We consider the peak of these signals, and the point is represented by p. At t is equal to 0, the point p is here. If we substitute any value which is greater than t, suppose t1, then this point, the peak point will move at these locations. At t greater than t is equal to t2, which is greater than t1, this point move like this. If you look at this point, then this point is moving in forward directions. This point is moving in forward directions. Or if you consider any point in this waveform, all the points is moving in forward directions. So we can say that the solutions of the above equations represents a traveling wave. The solutions of this equation, voltage or current expressions, represents the wave equations. The first term of this equations represent a wave which is moving in positive x directions, and the second term of this expressions, either you consider voltage or current, represent a backward wave which is moving in minus x directions. So at the end, after solving the voltage and current expressions, after getting the current and voltage expression in transmission line, if we find the solutions of voltage and current in transmission line, then we obtain two waves. One wave is moving in forward direction and another wave is moving in backward directions. In the next class, we will find the value of all the arbitrary constant v plus, v minus, I plus, I minus. Thank you.